evening. So we are in the second segment of the first lecture. The lecture is on probability theory, and in this segment we will be focusing on the topic of conditional probability. And let us motivate this topic by looking at a couple of scenarios. Now, the first scenario, suppose you look out of the window and it's a bit cloudy. Then what would you do? You would want to pick up the umbrella on your way out, because if it is cloudy now, then it's likely to be raining in a little while. Let's look at another scenario. What if a black cat runs across your path? Does that have any bearing on whether the day is going to be good or bad? Now, some of you may think that it may have a bad, it may be a bad omen, but scientifically speaking, there is no clear correlation between the two things. So these are just a couple of examples, situations where an event occurs and it may or may not have a bearing on some other event. And this notion of dependencies between events is what we're going to talk about today. So let's move towards making things a bit more formal. Suppose we know something about the outcome of an experiment. In particular, let's say we know that a particular event E has occurred. Now, does that influence the answer to the question, did some other event F occur? If the answer is no, then we say that the two events are independent, because now E has occurred, it has no bearing on whether F has occurred or not. And so they're said to be independent. On the other hand, now suppose the event E occurs, and that somehow changes the probability of F occurring or not occurring. Then we say that the two events are dependent on each other. This is an intuitive definition, but there's actually a more formal definition. So let's look at the more formal definition. Now we have two events E and F, and we want to know whether they're independent. When do we say that they are independent of each other? When the probability of the event E intersected with F equals the probability of E times the probability of F, then we say that two events are independent of each other. Another equivalent way of stating it is, of course, probability of E intersecting F divided by probability of E equals probability of F. Or yet another way would be to say probability of E intersected with F divided by probability of F equal to probability of E. Now, if you are anything like me, it doesn't immediately jump out to me as to why these two definitions, the intuitive definition and the formal definition, are equivalent. So let's try to reconcile the two definitions. Okay. And for this, we're going to interpret this left-hand side over here. Okay, so that's what we have over here. Probability of E intersected with F divided by the probability of F. So this division by the probability of F can be thought of as sort of a normalizing division, in which what we're doing is we are now restricting the sample space. So this division by F can be viewed as if F is the new sample space. Okay, so the probability space now looks like this. F is the entire space, and E intersected with F. Now previously, if you just recall the Venn diagram over here, there was the full sample space, there was F over here, E over here, and this of course E intersected F over here. Now the new sample space is just F, and we have just the part E intersected with F. So this is the new picture we get by looking at the left hand side. And a way to think of this is to think of it as though F has somehow already occurred, and because F has occurred, anything outside of F doesn't matter, and that's why the entire sample space is just F. And now we want to understand the probability of E. Now, as it turns out, there's actually a formal way to state this. This probability of E intersected with F divided by probability of F is also called the probability of the event E conditioned on F. So the condition is that F has already occurred. We know that F has occurred, and therefore under that condition, what is the probability of the event E? Okay, so this is denoted probability of E conditioned on F. Okay. Now that we have this insight into the left-hand side of that one particular formula, or the definition of independence, let's actually ask a few questions. Now, what does it mean when the probability of E conditioned on F is less than the probability of E? Now here, this is the probability under the restricted sample space. Now the sample space is just F, and we are asking what is the probability of E. On the right hand side is the probability of E in the full sample space of omega. Okay. Now if this probability of E given F is less, now that what does that mean? If you know that F has occurred, then the probability of the event E somehow is now less, is reduced. Similarly, when the probability of E given F is greater than the probability of E, then somehow under this conditioning on F, the probability of the event E has increased. In either of these cases, under the condition that F has occurred, the probability of event E has changed, and this is correlating with the intuition that we already have. So knowing something about the event F has a bearing on the event E, and so E and F cannot be independent of each other. On the other hand, now let's finally look at the case where probability of E given F is equal to the probability of E. Now under the condition that F has occurred, the probability with which event E occurs or does not occur is the same. It hasn't changed, and therefore now we can say that E does not depend on F. Okay. Now the question is, given that probability E given F is equal to the probability E, does this also mean the other way around, where probability of F given E is equal to the probability of F? Now what do you think? Try to work this out. This is an interesting question. Okay, now let's talk about an interesting and useful law that uses conditional probability. This law is useful in the context where we are interested in understanding the probability with which a particular event F occurs, but it occurs in somewhat of a complicated sample space, and we don't have quite a handle on the event F, but we have a way of, let's say, partitioning the sample space into lots of different events, E1, E2, and so on. And under these individual events, these disjoint events, we are able to understand something about F. Okay, so this is the picture we have. We have the sample space omega, and it's been partitioned into E1, E2, and so on up to E8 in this picture. And we have the event F, and the event F intersects with some of the EIs and not with all of them. And so what is this? So how do we now get an understanding of the probability of event F under this complicated scenario? Now the assumption here is that under each event EI, we have some understanding of the probability of F. So let's see how this plays out. So we're, as I mentioned, we're interested in the probability of the event F. And this probability, again going back to the very definition of probability function, should be the summation of the probabilities of F intersected with each of the EIs. Why? Because the EIs are all disjoint, and therefore F intersected with EIs, are all going to be disjoint, and together those events are going to, if you unite all of those events F intersected EI, they're going to equal F, and so their probability summed up should be the probability of event F, and this comes from the very definition of the probability function. Great. And now we simply notice that the probability of F intersected with an EI can be written as the probability of F given EI times the probability of E. Why is that? Well, you may recall that the formula for probability of E given F here is probability of E given F divided by the probability of F. We're just going to apply that formula here, and so this one is probability of F intersected with EI divided by probability of EI, and this just moving the probability of EI over to the other side, we get what we need. And so now, where does this law of total probability, as this law is called, where would it be useful? Now, as I pointed out a little while ago, it's useful whenever we have a handle on the probability of F given a particular event EI. And once we have such an understanding of F for each of the parts EIs, then we can put them all together and get an understanding of the total probability of the event F.